Good morning, everyone. Good morning, Dr. Chong. My name is Zhang Hanyi, and my student ID is AIT2409052. I will first introduce something about applications of derivatives in economics. And here is my contents. There are 8 parts in my presentation. The first part, the core role of derivatives in economics. There are 3 parts in measuring rates of change, derivatives in economic analysis, and marginal analysis, and optimization analysis. Okay. Elastic analysis, also 3 parts, price element of the demand, income elasticity of demand, and cross price elasticity of demand. Okay, the second part, cost analysis using derivatives. First, impact on production efficiency. A marginal cost derived from cost function helps in determining the additional cost of producing one more unit, which is essential for production planning and cost control. It aids in finding the most cost-effective scale of production and in making decisions about the expansion or construction of operation. Also, optimization of average cost. Derivatives assist in finding a minimal point of the average cost curve, which is critical for achieving economy of scale and reducing unit costs. Applications. Here are some applications. Okay, let's see a simple question. The total cost function of a company is given as CQ equal to 100 plus 20 times Q and plus 5 plus Q squared, where Q represents the number of unit products. We need to find Q. Marginal cost MC and find the minimal point of the average cost AC and the corresponding Q. If a company plans to increase production from 2 to 10 to 11 units, what is the implication of marginal cost for detection making? Okay, we can first find the something given as CQ and we derivatives, then we can find the marginal cost. When Q equal to 10, the marginal cost equal to 120 because the formula marginal cost equals to dc dq. Okay, then we can find the average cost is defined as AC equal to CQ over Q substituting CQ. AC equal to 100 over Q plus 20 plus 5Q. To find the minimum points, take the derivative of AC with respect to Q and set it to 0 dAC over dQ equals to this one. Then we let it equal to 0 and solving for Q, we can find this Q equal to square over 20. And we finally find the Q. This very easy for the implication of marginal cost for decision making. When the production increases from 10 to 11 units, the marginal cost is 120. This represents the additional cost of producing one more unit if the market price of the product is higher than 120. Producing the 11th unit is profitable. If the market price is less than 120, it is not cost effective to increase production. Well, let's start the revenue analysis using derivatives. Let's see what's the marginal revenue analysis. This is to determining sales value, benefits, and revenue maximization. Let's also see a simple question. The total revenue function of a company is RQ equal to 50 times Q minus 2 times Q squared, where Q responds to the number of units sold. We need to calculate the marginal revenue MR and determine the sales quantity Q. Let's maximize total revenue. If the company plans to increase sales from 10 to 11 units, that is the implication of marginal revenue for decision making. We need to calculate the marginal revenue MR. First, we need to use a formula M equals to dr over dq. It's very easy to derive it. It's just 50 minus 4q. Then when Q equal to 10, MR equal to also equal to 10. This indicates the selling the 11th unit will generate an additional revenue of 10. And that means the sale Q unit total revenue is maximized when marginal revenue equals 0. MR we let MR equals 0. Then we can find that Q equal to 12.5. Since sales quantity must be an integer, the company can choose Q equal to 12 or Q equal to 13 because we can find that Q is a circular. So its symmetry in Q equal to 12.5. So when sales increase from 10 to 11 units, the marginal revenue is 10. This indicates an additional revenue of 10 for each unit sold. If the additional revenue exceeds the cost of increasing sales, it's beneficial to increase sales. The first part, demand analysis and marketing happen. You can just see in here classifying demand elasticity and significance in decision making, also application in here. Okay, the five-find profit analysis using derivatives. It's also in marginal profit calculation. So we focus on decision making for production and pricing, profit maximization, and also some applications. Okay, the sixth part, we want to discuss production function and economy growth. Some original product analysis in production functions. First, assessing resource allocation efficiency. Second, economic growth applications. Third, applications. Yeah. And the seventh part, extension of derivatives in dynamic economics. Also three part, adjusting prices for maximize profit time series analysis using derivatives, risk assessment using derivatives of the three part. Then also sorry for this. Then see the example. We suppose that the cost of a factory producing X product is Cx equal to 2000 plus 100 times X minus 0.1 X squared ringgit. Its function Cx is called the cost function and the derivatives C dot x of the cost function. Cx is called marginal cost in economics. We need to try find two. First, the marginal cost when producing 100 units of product. Also compare the cost of producing the 101 product with the marginal cost obtained in one to explain the actual significance of marginal cost. So, we can find something given. The cost function is here, and the marginal cost function is just the derivative of Cx. So we just find the d and dx is just 100 minus 0.2 times x. When x equal to 100, it is equal to 80. And the cost of producing the 101 units, we can just use C101 minus C100. We're finding this is 79.9, and we comparison between them. Marginal cost at x equal to 100 is 80, and the actual cost of the 101 units 79.7. The two values are very close but not identical. Let me interpretation of it. The marginal cost C derivative x represents to approximate the additional cost of producing one more unit at production level x at equal to 100. The marginal cost is 80 currency units, which provide an estimate for the cost of the 101 units. The actual cost of the 101 units calculated as 79.9 currency units is slightly lower. This demonstrates that marginal cost is a useful approximation tool for evaluating cost changes with small increase in production. Okay, let's let me introduce the second example. We assume that the cost of a factory producing X units of a product is Cx equal to x cubed minus 6 times x squared and plus 15x. And the revenue from selling X,000 units of the product is Rx equal to 9 times x. Whether there is a method that can achieve the maximum profit production level, find the production level if it exists. We found the given situation, the cost function C8 here and the revenue function Rx here. So the profit function is just Px equals Rx minus Cx. We need to determine whether the production level X that maximizes profit, and if it finds a value. The profit function Pa just minus x cube plus 6 times x squared and minus 6x. We need to find the critical point, so we need to find the derivative of Px, and the d over dIPA is just this. So, and let we new derivative of P equals 0. We need to solve this. It's not a beautiful number. We can find that a1 equals to 2 minus square over 2, and a2 equals 2 plus square over 2. Okay, we need to determine maxima and minima. We need to find the derivative of p x, p dot x. You can see like this is just my negative 6 times x plus 2 over at 2 minus square over 2. It is bigger than 0, so x1 is a local minimum, and we also can find that x2 is a local maximum. We can find this the profit reaches its maximum at x equals to x2. Therefore, the optimum production level is x equal to 3.414. And you can also see the curve here. From the curve, we can find the local maxima and the local minima in economics. Derivative of Cs, what is Cs? Cx, Rx, and the Px is called marginal cost, and the derivative of Rx is marginal revenue, and the derivative of Ps is marginal profit. These above results show that at the production level that gives maximum profit. The derivative of Rx equal Cx, that is marginal revenue equals to marginal cost. The above result can also be seen from the cost curve and the revenue curve. Okay, let me summary it. It's not enough time, so please see on your, by yourself. Okay. Thank you very much. Okay, then let me introduce Washer method in calculus. It is a method for finding the value of solid of revolution. Okay, let's overview it. Its main idea is subtract the value of the hole from the outer solid, and the cross section of a washer is a ring with a hole. And the upper R is the distance from the outer curve to the axis of rotation, and the small r is the distance from the inner curve to the axis of rotation. You can see like this. Fex is the outer curve, and the F2x is inner curve. And how to if Fex and F2x rotation around the x-axis, how to find the value? We can see like this: the black one is the outer curve, and the blue one is the inner curve. If we want to find the value, we can calculate the bigger one and subtract it with the smaller one. We also can see the cross section is just a big circle and a small circle. We use the area of the big circle minus the small circle. We can also find the value. If the curve rotated around the y-axis, it's also the same. Just change to dy. Sorry for this. It's dy. Also, you can see the cross section is just a big circle and a small circle. And how to application proportion method? We have this step: first, identify the region; second, determine the axis; third, set up the integral. Let's see a question. We will calculate the value of solid of a revolution generated by revolving a region under one arc or of a circularity around the x-axis and the y-axis. The given parametric equation for the coordinate are x equal to a t minus sine t, and y equals to a plus 1 minus cosine t. Cosine, as we see the picture, is a curve about this function. You can see the graph, and then we want to find the value when region is revolved about the x-axis. We also want to find the value when region is rotated about y-axis. Okay, let's first see the easier one revolving around the x-axis. We can draw the picture first. We can see like this. The blue one is just the cross section. It's a circle, so it's easy to calculate, and we can integrate from 0 to 2 pi a for x, and pi times y plus you can see as the red one. Okay, then we change the dx to a minus 1 minus cosine t. Then we can find it. Please be careful. Here it's dt, so we should change from 0 to 2 pi a to from 0 to 2 pi. And we can calculate like this. There's the only thing we should be careful: the cosine cube t. We need to use the substitute and also change cosine square t to 1 minus sine square t. Then also you can see like this. We can find out each one. We can integrate it each one. Then we can find it's 5 pi. So bx equals to pi a cube times 5 pi. So bx is this. Okay, let's see the one which is more difficult. First, we need to see like this. Region is revolved about the y-axis. It's also the function here. Okay, this one is more difficult. Let's see the curve now. We need to revolve the curve about the y-axis, and you can see this is from 0 to 2a. It's difficult to see this, so we spare it into two parts, which is the green one and the red one. And we denote the green one x equal to xy, and the red one x equal to x1y. We need to use the green curve to minus the red one. So we can find like this. This one is from 0 to 2a, and pi x2 square y minus x1 square y. Then we choose y. Where is y? Where is y? Y is here. No. X is here. X equal to a times t minus sine t. We can find like this. Okay, it's the same. The two is same, so the difference is the interval, we need to be more careful in here, which one you can see from here, from the lowest point to the highest point. If you see in the x-axis, you can see it's from 0 to pi. So because we need to find from the x-axis to more higher than it, also how to say, move to the positive direction of y-axis, we must be careful. The green curve is moved from 2 pi to pi in x-axis. In y-axis, the two curve is the same, move from 0 to 2a, but in x-axis, the two is different. So we can find the green one is from 2 pi to pi, and the red one is just from 0 to pi. Then we need to calculate more carefully. You can see the more detailed steps in here. We need to converting to part t and simplifying the integrate and evaluate each one integral we need to calculate. Then we final calculation is equal to 6 pi square pi cube and a cube. Okay, so at one, the curve rotated around y-axis is more difficult. Okay, thank you very much. Then I will tell a moment and the center of mass. First, let's look what is a moment. A moment describes the distribution of mass relative to a reference axis. It reflects the rotational effect of mass distribution about the axis. For a one-dimensional continuous mass distribution, the moment is defined as the integral of the product of the mass element and its distance from the reference axis. A moment formula, moment about x-axis, this describes the rotation effects of mass distribution about the x-axis. Mx equal to y rho n ds integrate. In this formula, y equal to the distance of the mass element from the x-axis. Rho x is a mass distribution function, and ds is differential length. Also same about the y-axis, and the total mass. Total mass m equal to integrate rho x. Dn, this is the total mass of the object obtained by integrating the mass distribution function. Okay, what is the physical meaning? Significance of a moment. Moments measure the tendency of a mass distribution to cause rotation about a given axis. The farther mass is from the reference axis, the larger the moments. Moments are essential for analyzing the balance and the stability of objective. And also significance of the center of mass. The center of mass reference the equilibrium point of the object where the antimass can be thought of as concentrate. A relationship between moment and the center of mass. The center of mass is directly related to the moment. It is defined as the weighted average of the mass distribution relative to the reference axis. The calculation of the center of mass depends on the calculation of moment, which must be normalized by the total mass m. Let's see a question. The background, a uniform straight road of length L and a linear mass design mu lies along the y-axis. A point mass m is positioned on the x-axis at a particular distance a from the center of the road. The goal is to calculate the gravitation force exerted by the road on the point mass. Okay, let's see a situation which is given. A linear mass density of road mu. Mass of the point m is equals to m. Length of the road equals to L, and the distance of point M from the center of the road along the axis equals to A. Our object is to compute the horizontal component of the gravitation force Fa. Show that the vertical component of the gravitation force Fy due symmetry analyzes the gravitation force as the road length L approaches infinity. Okay, let's see the picture. We put a road in the y-axis, which is 0 in positive and negative L over 2. Then we choose one point randomly is y, and the distance from y to m is r, and from original O to m is a. Then we deposing into small elements. We can use the formula about a gravity F equal to g a big M plus a small m and over r square. It's like this because we only know the mu, so we need to plot it with its value, and we can see that r equal to a squared plus y squared is the distance between the segment of the point of mass m. Then horizontal force component. Gravitation force is a vector, so we need the horizontal component of df. The horizontal component is df and d equals to df plus cosine theta, and we can find the cosine theta in here. It's y over r, and the cosine theta we substitution r with a square plus y square underscore, and then the dimension tree is like this. Okay, the symmetry simplification. A road is symmetric about the x-axis. Every segment of above the x-axis there is a corresponding segment below it. For example, we can find y here and y uh y provide a false horizontal in n, and another point, a negative y, also provide a force to m in horizontal direction. So the two forces, since the two forces equal Fy equals to 0, then we only need to focus on horizontal force calculation. Fx equal to from negative L over 2 to L over 2. dFA equal to, we suppose Fa here is Fa is dFA. We find this formula because the integrand of symmetry about y equal to 0, we can simplify the integration range to the positive half of the root Fa equal to at least 1. And we need to solve the integrate and substitute this into Fa. Evaluate the definite integrate Fa equals to this and simplify it. We can find Fa like this. The fifth step, experiment case L approaches to infinity. When the root becomes infinity long, L equals to L approach infinity. For example, let me see. This L approach to infinity is very, 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 very long. What will we find? We can just find a squared plus 2 squared equal to 2 squared, because a is very, very small in here, so we can at least equal to L over 2. Substitute this approximation into the formula for fx. Fx equal to this, and we can find fx equal to 2g mu m over a. It shows that the root becomes infinity long. The gravitation force approaches a constant value. And how we can application this gravitation field calculations, these setups can be used to model the gravitation field created by linear mass distribution such as long rod or wires as written. Model infinity or very long linear mass distributions can approximate the gravitation effects of Canadian structures such as star corruption, for example, between Earth and Moon, and engineering analyzing gravitation intersection instruction with linear mass distribution such as beams or towers.